Welcome to today's presentation on psychometric functions. In this lecture, we're going to be talking about how we measure sensory activity and how we measure perceptual experiences. We're going to be talking very much about a branch of psychology called psychophysics. And in psychophysics, we are measuring the extent to which we can have a relationship between physical stimulation out here in the real world, that's physical stimulation in terms of acoustic energy or electromagnetic energy, whatever the physical energy might be, and its quantitative relation to our psychological experiences. So we can think of psychophysics as the science of establishing quantitative relations between physical stimulation and perceptual experiences. Okay? And to do that, we're going to be talking today about psychometric functions. There's an important parallel between psychometric functions and what we learned in a prior lecture on signal detection theory, and we'll see that relationship as we go on. Okay? So let's get right into it and talk a little bit about psychometric functions. Okay, so when we see this phrase, psychometric function, we'll unpack it a little bit. Psycho, as you might recognize, is simply the subjective or psychological experience that we have. Metric means to measure. And a function is something I'd like to define for us. So a function is a rule for turning one number into another number. We use functions all the time. One idea is that we can think of taking an average as a simple function. Many of us have had the experience of taking an average inside of, for example, Excel. And we'll have a list of numbers, and we might then have at the bottom of our list a unique cell where we type in something like equals average. We stick something in. We stick in, for example, a row of numbers. We might call that a vector of numbers, an ordered list of numbers, and we get something out. We get out an average. We might get out a median. We might get out a mode, whatever the case might be. Okay? So here we're talking about a psychometric function. A function is a rule for turning one number into another number. And what we're going to be doing is looking at, with respect to psychometric functions, we'll take in one number, a quantified stimulus. Again, we might have a quantification for how fast something is moving or how intense a sound is, whatever the case might be. We're going to take in a quantified stimulus as our input, and we'll turn it into another number, the probability of a behavioral response. Okay? So psychology is very much a behavioral science, and we want to see this relationship between a quantified stimulus and behavioral responses. So by convention, the physical quantity that we're going to have in our psychometric function will be represented on the abscissa. And for those of you who are not recalling, abscissa is a very fancy word for the x-axis. This is typically where our independent variable goes. And the behavioral response will be represented on the ordinate. That's the fancy word that we have, ordinate, for the y-axis or the vertical axis. That's typically where our dependent variable goes. Okay, so we have this idea of a psychometric function, and we have some idea about what's going to be going on what axis now. Okay. So here's a blank psychometric function, but it just gives us the chance to orient ourselves a little bit and understand what's going on which axis. So here's the physics axis, that's our abscissa, and we're going to have some relative stimulus values. Let me see if I can give you an example. Let's pretend that we're interested as sports psychologists in measuring how sensitive you are to detecting differences in how fast a baseball is coming at you. Okay? And if you imagine that you are in the major leagues in American baseball, it might be the case that pitches are coming at you at 90 miles an hour. So we're going to make 90 miles an hour a standard stimulus, and that would be represented right here on the center of our abscissa. Sometimes we're going to have our pitching machine throw you a baseball that's not coming at 90 miles an hour, but a little bit slower. That'll be on this side of the axis, or a little bit faster. So this would be, for example, 90 miles an hour, and this is 1 mile per hour slower than that, 2, 3, 4, and 5 miles per hour slower than that. So essentially this would be 89 miles per hour, 88, 87, 86, and 85. I've simply taken 90 and I've combined it with the values that you see on the left side of this axis. On the right side we have speed increments as opposed to speed decrements on the left side. So this would be 91 miles per hour, 92 miles per hour, 93, 94, and 95. Okay? So this is the physical speed of the baseball, and we're expressing this as the relative stimulus value. We've centered the 90 mile per hour fastball right here in the middle of our abscissa. Okay? Now we want to get some kind of behavioral response. At some point, we'd want to see if you could hit this baseball, but right now, we're going to engage in just the sensory task and the perceptual task of rating whether a particular fastball is faster or slower than the standard of 90 miles per hour. Okay? So we're going to give our participant two possible responses that they can make verbally. One is faster, and one is slower. Okay? And what we're going to do on the y-axis is we're going to plot the frequency of just one of those two choices. This is a type of experiment that we might call a two-alternative forced choice experiment. That's 2AFC, two alternative forced choice experiment. And there are two choices on this particular psychophysical experiment would be faster or slower. Okay? And we might choose to track one of those. By convention, we often choose to track just the increment response. In this case, we might think of that as the faster response on the faster, slower option. So we might track the proportion of trials on which the participant is reporting faster. Okay? And we might imagine then if we're going to get very low levels of that response when the stimulus is physically slower, and we'll get higher levels of that chosen response, in this case the faster response, when the stimulus is physically faster. Okay? So, what we're going to do now is give you some idea about some items that are relevant to the psychometric function. We're going to be very interested in the slope of the psychometric function and also the y-intercept. As you might imagine, for any linear function, as you might remember from 7th or 8th grade, y equals mx plus b, where y is going to be the particular value on our ordinate, m stands for the slope, b stands for the y-intercept. You have this kind of layout for a standard linear function. Okay? Standard linear function, something you're very familiar with. This is a little bit like that. It's going to have an important slope, our psychometric function. And we'll also have another concept called the x-intercept that we will come to shortly. But we're going to have now not a linear function, but something called a sigmoidal function. Again, that's pronounced sigmoid or sigmoidal if you use the adjective form. We're going to get a sigmoidal function as a description of our relationship between the physical stimulus and the response that the participant would make. And this formula is a much more complicated formula than what we have up here. But I think you'll still see some common elements. We'll have a slope, and now something called an x-intercept. You will not have to memorize this formula. So I hope that makes you feel relieved. You will not have to memorize this formula. But this is the kind of formula that we would use in a psychometric function to relate the physical stimulation to the sensory response. We call this a sigmoidal function. Okay, so we're going to talk first about one of three important aspects of the psychometric function. We'll talk about the slope. Later on, we'll talk about the x-intercept. And after that, we'll talk about something called the goodness of fit. So let's talk a little bit about slope first. Okay? So a psychometric function, or psychometric functions collectively, will vary one from the next depending on their slope. Some of them are going to have relatively steep slopes, others are going to have less steep slopes. And this is one of the ways that psychometric functions vary from each other. It's going to be variation in slope. And I think you'll find that these slopes have a very, very important psychological interpretation that we'll come to in just a little bit. Okay? The general rule that you'd like to remember is that steeper slopes correspond to better discrimination, also correspond to lower thresholds. So from Introduction to Psychology, when you took a section on sensation and perception, you might remember that there's this inverse relationship between thresholds and sensitivity. Okay? So if we have a very sensitive response, we'll have very, very low thresholds. Okay? So the thing to remember here is steeper slopes correspond to better behavioral discrimination. And in this sense, discrimination is a good thing. We want our sensory systems to be able to discriminate faster baseballs from slower baseballs, saltier water from less salty water, hotter stimuli from less hot stimuli. That kind of sensory discrimination is a good thing. We need to make sure that we're distinguishing sensory discrimination from discriminatory practices in our social lives, in employment and educational opportunities and healthcare outcomes and so forth. We want to make sure that we don't have discriminatory practices. But with respect to sensation and perception, discrimination is a good thing. Shallower slopes on our psychometric functions will indicate worse discrimination, which correspond to higher thresholds. Okay, so if your slope is infinite, Okay? We have a very, very steep function. We might even call that a step function. We step from the bottom of the graph all the way up to the top. Okay? That would be a step function. We have a ceiling effect. And this would imply that the discrimination task that we are asking our participant to complete is too easy. It's just too simple of a task, and this is something that the participant can judge very, very easily. To go to the other extreme, we can also have a zero slope. That's going to be a very, very flat slope. There's no tilt this way, there's no tilt that way. This is a flat function, and if this is the case, we have a floor effect. Your task is too difficult for the subject. We might be asking the subject to make a discrimination that their sensory system really can't make. Maybe we ask somebody who doesn't have a very good ear for music to hear the difference between one note on a violin and a slightly different note on that same violin, and their ear can't make that discrimination. This would be too difficult a task for this participant, and that being the case, we would actually wind up with a flat slope in our psychometric function. We're hoping that we can get, as experimental psychologists, some range of stimuli where we get relatively intermediate slopes. These are desirable, and they play another important role for us. For those of you who have had Psych 200 research methods, you might know that when you're trying to draw a causal inference, what you need to do is be able to eliminate alternative plausible possibilities as alternate explanations for a given phenomenon. And what's important about this idea of ruling out alternative explanations is that if we have an intermediate slope, we can see that the person's behavior is very much under stimulus control. That is, just a slight change in the stimulus might get a slight change in behavior. Another change in the stimulus might get a further change in behavior. When we have the stimulus control, or a stimulus-controlled relationship for the person's behavior, we can say that we can rule out objections for what's driving the participant's behavior. We can rule out, for example, cognitive interpretations. Maybe somebody is having a floor effect because they don't understand what we're asking them. If they don't understand what we're asking them to pull out of the stimulus, then that cognitive limitation might be generating a relatively flat function. And if it is generating a flat function, then we have at least two explanations, right? We could say that there's a cognitive limitation, or it could be that there's a sensory limitation. And maybe they understand what to be looking for, but their sensory systems can't pull that information out of the stimulus. So we're hoping that we get intermediate steps. We might think of this as something akin to the Goldilocks interpretation of psychometric functions. We don't want something that's too hot or something that's too cold. We want them to be just right. Okay, so let's take a look at a hypothetical psychometric function. And here we have the relative stimulus value. We'll go back to our recurring example of baseballs that are being thrown at us by a pitching machine. Some of these are faster than the standard, which we're centering at 0, just to keep things easy. If it helps you to think about this being the 90-mile-an-hour fastball, that's our standard. And then we get slower and faster ones. And we said a moment ago we would choose one of our two responses in our two alternative forced choice experiment. That's a 2AFC. We would choose the quote-unquote faster response. And here we actually have perfect performance. This individual, this hypothetical individual, has perfect performance. Every single time we throw this person a baseball that's faster than the standard 90 miles per hour, centered here at 0, this person always reports that as being faster for 91, 92, 93, 94, and 95 miles per hour. Okay? On the other hand, when we're on this side of the axis, this person correctly always reports slower when we have an 89, 88, 87, 86, or 85 mile per hour fastball. So they never report faster for a slower stimulus. This is absolutely perfect performance. And this would be an example of a step function. We're stepping from the bottom all the way up to the top. As soon as our stimulus crosses over from the physically slower side to the physically faster side. Okay, remember, this is 90 miles per hour. This is slower than the standard. This is faster than the standard. So this is actually too easy. Okay? Right? This, in our Goldilocks interpretation, would be too hot. This person's doing too well, and we have red shown here for red hot. Okay? Let's contrast that with another participant who's having the opposite problem. This participant, shown in blue, and in flat line, is really having trouble making a sensory discrimination on these baseballs. This person basically is guessing all the time, and if we have a really, really fast stimulus, a 95 mile per hour stimulus, Unlike the first participant, who always classifies that correctly, this person is just guessing. It's almost as if this person is blind to the speed differences that we have going across this axis. So the person guesses faster about 50% of the time, and they guess slower about 50% of the time, regardless of what's going on in the stimulus. So this person's behavior is not showing any sensitivity whatsoever to the physical variations that we have going on in our independent variable. They have no sensory sensitivity whatsoever. Okay? So this is too hot, this is too cold, and we have blue as the color for this particular participant because this person is ice cold. Okay? Too hot, too cold. But now we have in green a participant for whom this stimulus set is just right. Okay? You can take a look at that and you see this nice smoothly varying curve. That is, if we give this person a relatively exaggerated stimulus, 95 miles per hour, most of the time they report that as being faster. They almost never report the 85 mile an hour fastball as being faster, but as we make this speed slightly greater and greater, and actually then greater than the standard, we get a monotonically increasing response. Monotonic means one tone or one direction. We get ever increasing levels of faster responses for this green function. So what's going on here is that these three different participants are showing three different levels of sensory sensitivity. The person in blue has essentially no sensitivity whatsoever to the physical variations of the of the baseball that's coming in. The person in green is able to discriminate these really quite well. We're getting a change in behavior that corresponds rather reliably to the changes in the physical stimulation. And then in our red case, we have a person who's also showing great stimulus control, in fact, perhaps too exquisite a perceptual control, or stimulus control, excuse me. Stimulus control, this person is exhibiting a step function. Okay, so three very different kinds of slopes. One of the ways of thinking about slope and its relationship to sensitivity is that we want to see to what extent we get a change in behavior for a physical change over here. And many of us are familiar with the colloquial phrase that this little girl or this little boy makes a mountain out of a molehill. And what we mean by that is for a relatively small event, they have a very, very large response. Maybe they get very upset, maybe they get very anxious, they make a mountain out of a molehill. Okay? So for just a little bit of stimulus change, there's a big behavioral change. That's very much what goes on in a psychometric function. We want to measure your sensitivity. The participant shown in red here has a very large change in behavior for just a relatively small change on the x-axis. Okay? We can think of the slope here as a rise over run kind of equation. And we get a huge rise in behavior for a small run in the physical change. The person in green is less sensitive. We can get a rise, so to speak, out of that person, but we need to now change the stimulus more dramatically. And for the person shown in blue, we're not getting any change whatsoever when we change our physical stimulus. Okay? So a lot about slope here. Okay, so slope is one of three aspects, or three characteristics, that we will pull out of a psychometric function. And we're now going to go on to a second aspect of the psychometric function that is a little bit less familiar to you. Slope was probably something you understood fairly well. Here we have something called x-intercept. It's a little bit like the y-intercept, but also a little bit unique. So we'll walk ourselves through a couple of examples. The x-intercept gives us some different information than the slope does. And what we can see here is that for psychometric functions, they will vary from each other not only with respect to slope. We saw a moment ago the red, green, and blue slopes were all very different from each other. They can also differ from each other along this other dimension of variability. And this is called x-intercept. The x-intercept is an index of bias, an index of the point of subjective equality, or PSE. So this is a brand new term, and we'll see if we can come to understand it over this next couple of slides. To the extent that the x-intercept departs from the center of the abscissa, again, the abscissa is our x-axis, so to the extent that the x-intercept departs from the center of the abscissa, the center range of the stimuli that we're manipulating, for example, the speed of our stimulus, then we have some kind of a bias in our participant's response. And we can be very interested in measuring a participant's sensory sensitivity, but also their bias. So the slope that we measured a moment ago is an indicator of their sensitivity or their discrimination ability. Here, with our x-intercept, we're going to measure their bias, and we'll see a couple of examples of this. Okay. The PSE is equal to the abscissal value, that's the value on the x-axis, that's our quantified stimulus, that is associated with the 50% ordinal value, that's half the way up on our y-axis. Okay, so we'll walk you through that in just a moment. But just so you have the idea of the PSE, or the point of subjective equality, and psychologists are very interested in measuring points of subjective equality. The PSE is equal to the abscissal value that is associated with the 50% ordinal value. Okay, so let's see if we can take an example here. This person shown in green is somebody who has a relatively nice slope, and they have basically no bias. Let's see if we can understand why we say that they have no bias, why their PSE is near zero. You remember from the prior definition that we want to go to halfway up on our ordinate, that's going to be the 0.5 value, and we're going to march across. And then we're going to drop down, and we're going to be right at zero. Okay? So what we have is an x-intercept that corresponds to zero. The 50th percentile here, or the 0.5 response rate, corresponds to an x value of zero. In our hypothetical, that would be 90 miles per hour. Okay, that's the standard stimulus. When we present this person with a standard stimulus, they are 50% likely to say faster and 50% likely to say slower. This is the point at which they're using those two response options with equal probability. Okay, so we infer that this is the point of subjective equality. All right, now let's go ahead and add a different participant. I'm going to show this participant in red, and what you'll see here is that we're getting maybe a very similar kind of slope. If I can ask you to imagine that you're going skiing down this slope and skiing down this slope. The slopes are pretty similar, but clearly the person shown here in red is exhibiting a very different kind of behavior. Let's play our rule one more time. We start at 0.5, we march over, we march down, and now we're getting a point of subjective equality, or an x-intercept, equaling -3. So let's see if we can interpret this now. From a psychological perspective, we might say this. The person who is shown here in green perceives the center of this distribution of physical stimulation about correctly. That is to say that they see the 90-mile-an-hour fastball as being the 90-mile-an-hour fastball. The person in red, though, has a systematic bias. They're estimating that this stimulus, which would be the 87-mile-per-hour fastball, here's 90, here's 89, 88, 87, they are responding 50% of the time faster and 50% of the time slower when we present them this stimulus. That's their point of subjective equality. So they have a bit of a bias. They have a nice slope for us, but they're biased, they're a little bit too inclined to say faster. We might even say that with respect to their faster response option, they have a liberal response bias. They're saying faster much more frequently than they should. Okay? Let's take another example, just so you can sometimes learn by contrast. Here's somebody shown in blue, okay? And we're going to play the same game as we played before. We'll start at our point of neutrality on this axis, okay? The point at which you're equally likely to say faster or slower. Okay? 0.5, we march on over, and we march down, and we wind up with a +3 value. So this person has a slope that's roughly comparable to the other slopes, but they have a very different kind of bias. This person is much more conservative with their use of the phrase faster. Okay? Remember that they have the faster and slower response options. And now they're understanding that it may be a 93-mile-per-hour fastball. They're perceiving a 93-mile-per-hour fastball as being at about the center of their distribution. So the physical distribution is centered here, and that corresponds to what the green participant is doing. But our red and blue participants have equal but opposite kinds of biases. One is relatively liberally biased with respect to his or her use of the faster response. The other is relatively conservatively biased. And yet all three of these persons, if I could extend these just a little bit further off to either side, would have very, very comparable slopes. So So I'm going to try to draw this for us now. I'm going to put the screen up and see if we can take a look at how you might draw this on a test. Okay? So I'm going to break out of that. I'm going to put up a slide just for a moment that will take away projection. Okay. And I will draw for us a psychometric function. Okay, so we can have basically any values that we want along here. We can have tones that are sharper or flatter. We can have baseball pitches that are faster or slower. Okay, we're going to center this at 0. And we typically have 1 through 5 over here, minus 1 through 5 over here. If that's too small to see, I apologize for that, but if you're playing along at home and you're drawing these out, that's 0, 1, 2, 3, 4, 5, and then we're going to have negative 1 through 5 over here. Okay, and this is going to be the proportion of the chosen response. We'll stay again with our baseball example, where we have a baseball coming in at 90 miles an hour and either slower or faster than that. What we're going to draw is 3 different psychometric functions, one that has a relatively neutral response bias, one that has a liberal, and one that has a conservative response bias. So you can almost think of this as an airplane that's going down a runway, takes off, and then eventually has elevating height that levels off at some point. So I'll draw something like this. Okay, we might call that our first airplane. All right. Now I'm going to draw a similar kind of trajectory, but one that has, if you will, a liberal response bias. So we're going to start out just like this, but we start to take off a little bit sooner, and we hit the same elevation, but we get there just a little bit sooner, not because we have a steeper slope. These slopes are about the same as each other, but we had a different point of takeoff, so to speak. I'll draw one more. It has, again, a fairly comparable slope. Okay? Those slopes are relatively similar to each other, but now we have a conservative displacement rightward of center and a liberal displacement this way of center, left of center. Okay? So you should be able to draw these psychometric functions with a common slope and with 3 different kinds of biases. If you can do that, you have some mastery over psychometric functions, and you're able to extract from psychometric functions this important concept of bias. Sometimes our people will differ from each other, or our non-human animals will differ from each other with respect to bias. Okay, so let's bring back the slides. And we'll talk about the third concept that is relevant to this measurement of psychometric functions. We've already talked about slope. Just to review a little bit, Slope told us about how sensitive our folks are to changes in the stimulation that we have on our x-axis. Okay? Then we also noticed that we can have a bias. Some people might be inclined to say faster or inclined to say slower in a way that has no bearing on the actual slope of their psychometric function. Okay? Now we're going to talk about something called goodness of fit. And some of us from Intro to Psych or Psych 200 research methods might remember that there's a goodness of fit statistic called the chi-square. There are other statistics we can use too to measure the goodness of fit. One of them is the R statistic, and we'll show that in just a moment. Just to retain some parallel with our earlier sections, we can remind ourselves that psychometric functions vary from each other with respect to goodness of fit. So this is now the third dimension of variability. We had slope, we had x-intercept, which corresponded to the point of subjective equality, or a person's bias, and now we also have a goodness of fit variation. Right? To the extent that data points, or their error bars, those little extensions that tell us the typical range over which we would observe that particular behavior, the extent to which data points fall near the psychometric function, the fit is good. Okay? So if we have points right on the psychometric function, we have a very good fit. If they're not right on the psychometric function, we have a less good fit. The goodness of fit can be indexed by the correlation, R statistic, between the data and the function. The function is simply the curved line that we draw, okay, which had that very fancy equation which you don't have to memorize. If the fit, that is, if the R statistic is statistically greater than would be expected by chance, and we use our p less than 0.05 standard, as we often do in all of the sciences. We learned about that in Intro to Psych. And we can be confident in estimating thresholds and points of subjective equality from the psychometric functions. Okay, so let's see if we can take a look at a few of these. Here's the proportion of chosen response, we've seen that before, relative stimulus value. We're still looking at the case where we have baseballs that are coming in faster or more slowly than 90 miles an hour. Okay? And here's somebody who has a relatively modest slope. We're not getting a real good bend. It's almost a straight line here, but this person is exhibiting some sensitivity to the change that we have in our physical stimulation. So what we can say is that each one of these data points, a datum would be the singular of data, is landing exactly on that solid line, on that blue line. Okay, this is a really good fit. We're getting an R value, R with 8 degrees of freedom, because we have a total of 10 of these observations, and the degrees of freedom would be number of observations minus 2 in this particular case. Okay, so we have 8 degrees of freedom. Our R value is right on track. R squared is therefore positive 1, and the probability of this occurring by chance is much less than 0.01. So this is a really nice fit. Okay? We have a good fit. We have a point of subjective equality that's right about here. We have a non-zero slope. We have a really good fit. Okay? Let's see if we can give you another example. Here we have a slope roughly comparable to what we had a moment ago. We have a point of subjective equality, maybe not too differently from what we had a moment ago. The salient feature, though, in this graph is that unlike the one before it, which is shown here, these green items are now dispersed, sometimes above, sometimes below this best fitting line, or the best fitting function. So now the R value, although acceptable, isn't really that strong. We still have 8 degrees of freedom, but the R value goes to 0.72. You might recall from Intro to Psych that R values typically range, or will always range, from -1 to +1, with a 0 indicating that there's no correlation between the two variables. We're trying to understand to what extent we have an orderly relationship between this variable and this variable, okay? Our behavioral or psychological variable and the physical stimulation. And there is a relationship there, but it's not really strong. It's maybe marginally smaller than 0.05 as a probability. We can square that 0.72, and we can say that we have a 0.53 R squared value. That would imply that this function, this best fitting green line, is accounting for 53% of the variation in the scores that we have. And the scores, again, are a plot of the chosen response, the proportion of faster responses that the person is making. Okay? So we've had a really good fit, and now we have a pretty good fit. It's an acceptable fit. Here's a case where we really have essentially an unacceptable fit. There's still a slope that's greater than 0, and we can move over from 0.5 and drop down as usual, get our x-intercept, or a point of subjective equality, an indicator of bias. But we can also see now that many of these red dots are nowhere near the best fitting line. Some of them are on, so we do get a R value that's greater than 0, but maybe not significantly greater than 0. The NS here corresponds to not significantly greater than 0. Okay, so the R squared now is 0.33. We're only accounting for 33% of the variation in the behavior that you and I as psychologists are tracking. And so there's only a very weak, maybe even non-significant relationship between our physical manipulation and the behavioral response that we're observing. Okay, here's another example that we have for the goodness of fit. And what we'll do is remind ourselves of a laboratory exercise that I had conducted in one of my first years here at Denison. To give you one additional example, we have on this axis a relative duration, and we asked our participants to judge how long a stimulus was relative to a 5-second standard. So our 5-second standard was positioned here. And then we also had stimulus conditions that were half a second shorter than 5 seconds, so that would be 4.5 seconds, or 1 second shorter, 4 seconds, or 1.5 seconds shorter than 5 seconds. That would be 3.5 seconds. On this side, we have longer durations of time. This would be 5.5, 6, and 6.5. Okay? And what we asked them to do is report that a particular duration was longer or shorter than the standard 5-second duration. Right? So estimating time is something that we do all the time, and sometimes we estimate time on the order of months or years, sometimes on the order of milliseconds. We estimate time over many, many different scales. Here, it's approximately a 5-second scale that we're measuring, and we wanted to measure their psychometric functions across this range of physical stimulation. Another independent variable that we had in this case was a bias control. That is, we told the participants on some conditions that when they were in doubt about whether a stimulus was longer than 5 seconds or shorter, when in doubt, they should say longer. Okay? And we gave them some kind of a penalty if they didn't. We gave them some kind of a reward if they did. So we tried to bias them towards saying longer. And in another experimental condition, we had the same participants, but we wanted to bias them in the opposite direction. When in doubt, say shorter. And this is often the case in real-life situations. There might be a penalty for making a particular mistake in one direction that's a steeper penalty than making a mistake than for making a mistake in another direction. Okay? So we can introduce a skew, so to speak, in their bias, and we should see then left and right departures in the center point for these psychometric functions. So we can take a look at these two, and we see that they're roughly comparable in slope. You can imagine going skiing down each of these. I think the yellow one is just a little bit steeper. So in this yellow condition, it looks like performance was just a little bit more precise. We can think of the precision of the responding as corresponding to its slope. So I'd like you to make a note of this. Precision corresponds to the fineness of a measure. I'll say it again. Precision corresponds to the fineness of a measure. And here, for a relatively fine change in the x-axis, which would be the relative duration, we're getting a really strong change in the behavior. Okay? So we have some level of precision here because we have, over very fine units of physical stimulation change, we have a big change in behavior. Okay? So we're getting greater precision or greater slope in our yellow condition than we are in our red condition. Now let's go to the second of three aspects by which we might distinguish these two conditions. And our second aspect is this point of subjective equality. It's a measure of bias. And we can now move over from 0.5 to here and drop down. And we're getting some level of stimulus duration that is a little bit to the left of center. Okay? So when in doubt, say longer. And we created a bit of a liberal response bias to saying longer here. Okay? And then we can do the same thing for the yellow condition. We move over and drop down. And they were just about neutral there. Okay? When in doubt, say shorter. Okay? So the probability of a longer response went down. And we can see that by the rightward shift in these psychometric functions. So these are shifted leftward and rightward from each other. So they differ from each other in two ways. The yellow one is ever so slightly more steep. That gives us a greater fineness of measure. Okay? That's greater precision in the yellow case. Okay? And then we also have leftward and rightward shifts that are driven by the instructions we gave to our participants, and we altered their bias. I'd like you to now jot down another definition. And this is the definition of the word accuracy. We measure accuracy lots of ways. Percent correct is a very commonly used measure of accuracy. But we can think of accuracy as the extent to which an observation departs from a standard. Accuracy is the extent to which an observation departs from a standard. Okay? So the standard might be thought of as 0, and we have, in the yellow case, relatively little departure from that standard. Okay? By contrast, in our red case, when we asked our participants to say longer when they were in doubt, we created a bit of a bias, okay? And we have now a reduction in accuracy. The actual standard is right here. We've moved their response a little bit over this way. So we've introduced a bias, we've introduced an inaccuracy. These two curves are showing roughly the same levels of precision, although the yellow bit is a little bit more, the yellow line is a little bit more precise than the red line. But they're actually quite different from each other in accuracy. The yellow line is relatively right on target, okay? Not departing very much from the standard, and the red one now is quite a bit leftward of the standard. So we can think about the distinction between accuracy on the one hand, that's indexed by the bias or the point of subjective equality, the x-intercept, okay? Or we can think of the precision, and that's given by the slope. That's going to be a measure of their sensitivity to the stimulation. Okay. So let's go on to a learning check. And for your next class, and you might want to do this before coming into class, I hope you can do this. On one plot, it's just one simple Cartesian grid where you have behavior on this axis, and physical stimulation on this axis. I hope you can take one plot and draw two psychometric functions that differ from each other in slope or discriminability. Thinking back to what we learned in signal detection theory, greater slope will actually correspond to higher levels of D prime. So a steep slope would have a really big D prime, a shallow slope would have a much smaller D prime. Okay? So we have one plot, and we have a relatively steep slope and a relatively narrower slope. Okay? Another exercise would be on a different plot, draw two psychometric functions that differ from each other only in midpoint. So these two have the same slope, or nearly so, but they're quite different with respect to their midpoint or their point of subjective equality. So one might have a relatively leftward shift, one might have a relatively rightward shift, and this would be a difference in accuracy, the extent to which these functions are departing from a standard. By contrast, this first exercise would be an exercise in precision. We're trying to show that one of our participants has greater precision, greater discriminability, greater D prime to the stimulus than does a different participant. Back here, when we're talking about the point of subjective equality, we might harken back to signal detection theory and remind ourselves of the criterion. We had criterion shifts that indicated a relatively liberal response bias or a relatively conservative response bias. Okay? Same thing is going on here with our points of subjective equality. And finally, we might end with a third plot where we draw two psychometric functions that differ from each other only in goodness of fit. So here we would have two curves that are equally steep. They're equally centered or equally off-centered. Whatever their x-intercept might be, it is the same for the first one as it is for the second, but one of them will have a really, really nice fit to the data, the other will have data points scattered a little bit afield from where the best fitting line is. So we have three different features that we can pull out of any one graph. Okay, and just to wrap up, what I would like to do is give you a summary conceptually of what we've talked about so far. And this might be a little bit simplistic, but I think it will help you remember things. So when we're looking at psychometric functions, we're really going to be able to pull out three pieces of information. What is the slope? That tells us about discriminability or their precision. What is the x-intercept? That tells us about their bias, the point of subjective equality. Okay? This is related to their accuracy, the extent to which they're departing from a standard. And then third, we have this other feature that we call goodness of fit. How well are the data points lining up on the best fitting lines? Let's harken back to something that we learned way back in kindergarten or even earlier, when you were a very young child and you were trying to learn about shapes and sizes and colors. An aunt or an uncle might have come up to you and said, here are three images, which one is biggest? Okay? And you would look at these and you would say, well, this one is the biggest. Okay? You can look at exactly that same stimulus and have a very different kind of response if the question had been, which one is red? You would point to this one. Okay? And you might be asked the question, which of these is triangular? Okay? And you would point to that one. Okay? So one stimulus can differ in at least three different dimensions. There can be color differences, there can be size differences, and there can be shape differences. This is a trivial example, but thinking back to our psychometric functions, we can say the same thing about psychometric functions. They too can differ in three dimensions. They can differ in slope, they can differ in x-intercept, and they can differ in goodness of fit. And all three of those pieces of information tell us something about the relationship between physical stimulation out here in the world and our psychological experiences. I'd like to close with one last definition, and this is the definition of information. Information can be defined as the reduction of uncertainty. If you have information about a stimulus, you are less uncertain about that stimulus in some way. If you have information about your schedule for the semester, you have less uncertainty about your schedule for the semester. If your professor gives you information about the test, what kinds of things to study, what kinds of things not to study, the professor has reduced uncertainty about that test. In our endeavors as experimental psychologists this semester, we're trying to reduce uncertainty about what we can say regarding our sensory sensitivity. And we can do that along three dimensions. We can do that along the dimension of slope or precision, or the sensitivity of a response to different physical stimulation. We can talk about biases, as indicated by the x-intercept, and we can also talk about the goodness of fit. How well does one of these psychometric functions fit the data set? So I hope that you'll turn the projector off now and look at the PowerPoints and see if this all makes sense to you, and come into class with some questions ready to go. See you in class.